The preflow push maximum flow algorithm. From the very beginning, our discussion of the maximum flow problem has been centered around the idea of an augmenting path in the residual graph. However, there are some very powerful techniques for maximum flow that are not explicitly based on augmenting paths. In this section, we study one such technique, the preflow push algorithm. Designing the algorithm. Algorithms based on augmenting paths maintain a flow f and use the augment procedure to increase the value of the flow. By ways of contrast, the preflow push algorithm will, in essence, increase the flow on an edge-by-edge basis. Changing the flow on a single edge will typically violate the conservation condition, and so the algorithm will have to maintain something less well-behaved than a flow, something that does not obey conservation as it operates. Preflows. We say that an ST preflow for short, is a function f that maps each edge e to a non-negative real number, f which maps from e to r plus. A preflow f must satisfy the capacity conditions. That is, 1 for each h e in E, we have 0 less than equals to f of E less than equals to CE. In place of the conservation conditions, we require only inequalities. Each node other than S must have at least as much flow entering as leaving. 2. For each node V other than the source S, we have the summations of Fe summing for all E into V is greater than equals to the summations of f of E summing for all E out of V. We will call the difference EF of V equals to the summations of f of E summing for all E into V minus the summations of f of E summing for all E out of V. The axis of the preflow at node V. Notice that a preflow where all nodes other than S and T have zero axis is a flow, and the value of the flow is exactly EF of T equals to minus EF of S. We can still define the concept of a residual graph GF for a preflow F just as we did for a flow. The algorithm will push flow along edges of the residual graph using both forward and backward edges. Preflows and labelings. The preflow push algorithm will maintain a preflow and work on converting the preflow into a flow. The algorithm is based on the physical intuition that flow naturally finds its way downhill. The heights for this intuition will be labels h of v for each node v that the algorithm will define and maintain, as shown in figure 7.7. We will push flow from nodes with higher labels to those with lower labels, following the intuition that fluid flows downhill. To make this precise, a labeling is a function h which maps from v to z, which is greater than or equals to 0, from the nodes to the non-negative integers. We will also refer to the labels as heights of the nodes. We will say that a labeling h and an st flow f, st preflow f, are compatible if 1. Source and sink conditions, h of t equals to 0 and h of s equals to n. 2. Steepness conditions. For all h's vw in EF in the residual graph, we have h of v which is less than or equals to h of w plus 1. Figure 7.7, a residual graph and a compatible labeling. No edge in the residual graph can be too steep. Its tail can be at most 1 unit above its head in height. The source node S must have h of s equals to n and is not drawn in the figure. Intuitively, the height difference n between the source and the sink is meant to ensure that the flow starts high enough to flow from S toward the sink T, while the steepness condition will help by making the descent of the flow gradual enough to make it to the sink. The key property of a compatible preflow and the labeling is that there can be no ST path in the residual graph. 7.21. If ST preflow F is compatible with the labeling H, then there is no ST path in the residual graph GF. Proof. We prove the statement by contradiction. Let P be a simple ST path in the residual graph G. Assume that the nodes along P are S, V1, V2, V3 until Vk equals to T. By definition of a labeling compatible with preflow F, we have that H of S equals to N. The Hs V1 is in the residual graph, and hence H of V1 is greater than or equals to H of S minus 1, which is equals to N minus 1. Using induction on I and the steepness condition for the H V minus Vi minus 1 Vi, we get that for all nodes Vi in path P, the height is at least H of Vi, which is greater than or equals to N minus I. Notice that the last node of the path is Vk equals to T. Hence, we get that H of T is greater than or equals to M minus K. However, H of T equals to 0 by definition, and K less than N as the path P is simple. This contradiction proves the claim. Recall from 7.9 that if there is no ST path in the residual graph GF of a flow F, then the flow has maximum value. This implies the following corollary. 7.22. If ST flow F is compatible with the labeling H, then F is a flow of maximum value. Notice that 7.21. If ST preflow is compatible with the labeling H, then there is no ST path in the residual graph GF. So note that 7.21 applies to preflows, while 7.22 is more restrictive in that it applies only to flows. Thus, the preflow push algorithm will maintain and the labeling H compatible with H, and it will work on modifying F and H so as to move F toward being a flow. Once F actually becomes a flow, we can invoke 7.22 to conclude that it is a maximum flow. In light of this, we can view the preflow push algorithm as being in a way orthogonal to the Ford-Fulkerson algorithm. The Ford-Fulkerson algorithm maintains a feasible flow while changing it gradually toward optimality. The preflow push algorithm, on the other hand, maintains a condition that would imply the optimality of a preflow F if it were to be a feasible flow, and that the algorithm gradually transforms the preflow F into a flow. To start the algorithm, we will need to define an initial preflow F and a labeling H that are compatible. We will use H of V equals to 0 for V not equals to S and H of S is equals to N as our initial labeling. To make the preflow F compatible with this labeling, we need to make sure that no edges leaving S are in the residual graph, as these edges do not satisfy the steepness condition. To this end, we define the initial preflow as f of e equals to ce for all edges e equals to sv, leaving the source, and f of e equals to 0, or for all other edges. 7.23. The initial preflow f and the labeling h are compatible. Pushing and relabeling. Next, we will discuss the steps the algorithm makes toward turning the preflow f into a feasible flow while keeping it compatible with some labeling h. Consider any node v that has access, that is, f of v is greater than 0 if there is any HE in the residual graph GF that leaves v and it goes to the node w at a lower height. Note that h of w is at most 1 less than h of v due to the steepness condition. Then we can modify F by pushing some of the excess flow from V to W. We will call this a push operation.
Flow from V to W.
Push operation with input parameter F, H, V, and W. Applicable if EF of V is greater than 0, H of W is less than H of V, and VW is in EF. If E is equals to VW is a forward H, then let delta equals to the minima chosen among EF of V and CE minus F of E, and increase F of E by delta. If VW is a backward H, then let E equals to W, V, the reverse direction, and let delta equals to the minima chosen among EF of V and F of E, and decrease F of E by delta. Now, after we finish these two if blocks, we return FH. If we cannot push the axis of V along any H leaving V, then we will need to raise V's height. We will call this a relabel operation. Relabel of FHV applicable if EF of V is greater than 0, and for all H's VW is in VF, we have H of W is greater than or equals to H of V. Increase H of V by 1 and return FH. The full preflow push algorithm. So in summary, the preflow push algorithm is as follows. Preflow push. Initially, H of V is equals to 0 for all V not equals to the source S, and H of S is equals to N, and F of E equals to CE for all E which is equals to SV, and F of E equals to 0 for all other H's. Now there's a while loop. While there is a node V not equals to T with the axis EF of V which is greater than 0, let V be a node with axis if there is a W such that push of FHVW can be applied, then push FHVW, else we relabel FHV, else while. Then after we break out from the while loop, we return F. Now analyzing the algorithm. As usual, this algorithm is somewhat underspecified. For an implementation of the algorithm, we will have to specify which node with access to choose and how to efficiently select an edge on which to push. However, it is clear that each iteration of this algorithm can be implemented in polynomial time. We will discuss later how to implement it reasonably efficiently. Further, it is not hard to see that the preflow F and the labeling H are compatible throughout the algorithm. If the algorithm terminates something that is far from obvious based on its description, then there are no nodes other than T with positive access, and hence the preflow F is in fact a flow. It then follows from 7.22 that F would be a maximum flow at termination. We summarize a few simple observations about the algorithm. 7.24. Throughout the preflow push algorithm, 1. The labels are non-negative integers. 2. F is a preflow, and if the capacities are integral, then the preflow F is integral. And 3. The preflow F and labeling H are compatible. If the algorithm returns a preflow F, then F is a flow of maximum value. Proof. By 7.23, the initial preflow F and labeling H are compatible. We will show using induction on the number of push and relabel operations that F and H satisfy the properties of the statement. The push operation modifies the preflow F, but the bounds on delta guarantee that the F returned satisfies the capacity. of the capacity constraints and the excesses all remain non-negative. So F is a preflow. To see that the preflow F and the labeling H are compatible, note that push of FHVW can add one H to the residual graph, the reverse HVW, and this H does satisfy the steepness condition. The relabel operation increases the label of V and hence increases the steepness of all H's leaving V. However, it only applies when no H leaving V in the residual graph is going downward, and hence the preflow F and the labeling H are compatible after relabeling. The algorithm terminates if no node other than S or T has access. In this case, F is a flow by definition, and since the preflow F and the labeling H remain compatible throughout the algorithm, 7.22 implies that F is a flow of a maximum value. Next, we will consider the number of push and relabel operations. First, we will prove a limit on the relabel operations, and this will help prove a limit on the maximum number of push operations possible. The algorithm never changes the label of S, as the source never has positive access. Each other node V starts with H of V equals to 0, and its label increases by 1 every time it changes. So we simply need to give a limit on how high a label can get. We only consider a node V for relabel when V has access. The only source of flow in the network is the source S, hence intuitively the access at V must have originated at S. The following consequence of this fact will be okay to bounding the labels. 7.25. Let F be a preflow. If the node V has access, then there is a path in GF from V to the source S. Proof. Let A denote all the nodes W such that there is a path from W to S in the residual graph GF, and let B equals to V minus A. We need to show that all nodes with access are in A. Notice that S is in A. Further, no H's E equals to XY, leaving A can have positive flow, as an H with f of E greater than 0 would give rise to a reverse HYX in the residual graph, and then Y would have been in A. Now consider the sum of excesses in the set B, and recall that each node in B has non-negative access, as S is not equal to B. 0 is less than equal to the summations of EF of V, summing for all V in B, which is equal to the summations of F to the in of V minus F to the out of V, summing for all V in B. Let's rewrite the sum on the right as follows. If an HE has both ends in B, then f of E appears once in the sum with a plus and once with a minus, and hence these two terms cancel out. If E has only its head in B, then E leaves A, and we saw above that all H's leaving A have f of E equals to 0. If E has on its tail in B, then f of E appears just once in the sum with a minus sign. So we get that 0 is less than equals to the summations of EF of V, summing for all V in B, which is equals to minus of minus times F to the out of B. Since the flows are non-negative, we see that the sum of the axes in B is 0. Since each individual axis in B is non-negative, they must therefore all be 0. Now we are ready to prove that the labels do not change too much. Recall that N denotes the number of nodes in V. 7.26. Throughout the algorithm, all nodes have H of V, which is less than or equals to 2n minus 1. Proof. The initial label H of T equals to 0 and H of S equals to n do not change during the algorithm. Consider some other node v which is not equals to s and which is not equals to t. The algorithm changes v's label only when applying the relabel operation. So let f and h be the preflow and labeling returned by a relabel of fhv operation. By 7.25, there is a path p in the residual graph gf from v to s. Let the size of p denote the number of edges in p, and note that the size of p is less than or equals to n-1. The steepness condition implies that height of the nodes can decrease by at most 1 along each edge in p, and hence h of v minus h of s should be less than or equals to the length of p, that is, the number of edges in p, which proves the statement. Labels are monotone, increasing throughout the algorithm, so this statement immediately implies a limit on the number of relabeling operations. 7.27. Throughout the algorithm, each node is relabeled at most 2n-1 times, and the total number of relabeling operations is less than 2n squared. Next, we will bound the number of push operations. We will distinguish two kinds of push operation. A push of FHVW operation is saturating if either E equals to VW is a forward edge in EF and delta equals to C minus F of E, or VW is a backward edge with E equals to WV and delta is equals to F of E. In other words, the push is saturating if after the push the edge VW is no longer in the residual graph. All other push operations will be referred to as non-saturating.
7.28. Throughout the algorithm, the number of saturating push operations
the number of saturating push operations is not at most 2n times
in the residual graph.
Proof. Consider an HVW of in the residual
operation. We have
graph
h of v
after a
equals to h of
saturating
w plus 1
push
and the HVW
operation. We have
no longer in the
h
residual
of
graph
v is
GF
equals to
as
h
shown
of
in figure
w plus 1,
7.8.
and the HVW is no longer in the residual graph
Before
GF
we can push
as
again
shown
along this
in
edge,
figure
first we have to push from W
7.8.
to V to make the HVW appear
Before
in the
we can
residual
push
graph.
again
However,
along
in
this
order
edge,
to push from W
first
to
we
V,
have to
refers
push
the
from
need for
W to
W's
V to
label
make
increase
HVW
at least
appear in the
2.
residual graph.
So that
However,
W
in
is
order to
above
push
V,
from W to
the
V,
label of
we
W
first
can
need
increase
for
by 2
W's
at most
label
n
to
minus 1
increase
times.
by at least
So
2,
a
so
saturating
that
push
W
from V to
is
W
above V.
can occur at
The
most n
label
times.
of W can
Each
increase by
edge
2
in
at
E can
most
give
n-1
rise
times.
to 2 edges
So
in
a
the residual graph.
saturating path
So
from V
overall, we
to
can
W
have at most
can
2
occur at
nm
most n
saturating
times.
pushes.
Each edge little in capital E can give rise to 2 edges
The hardest
in the
part of
residual
the
graph.
analysis
So
is
overall,
proving a
we
bound
can
on the
have
number
at
of
most
non-saturating
2n
pushes.
times m
And this
saturation
also will
pushes.
be the bottleneck for the
Hardest
theoretical
part
bound
of
on
the
the running time.
analysis is proving about a number of
Throughout the
non-saturating
algorithm, the number
pushes.
of
And
non-saturating
this also
push
will be the
operations
bottleneck
is
for
at
the
most
theoretical
2n
bound
times
on the
m.
running time. 7.29.
For
Throughout
this
the
proof, we'll
algorithm,
use
the number
a
of
so-called
non-saturating push
potential function
operations
method.
is at
For
most
a Preflow
2n
f
squared
and a
times
compatible labeling h, we define a phi of fh
For this proof, we will use a so-called potential
v such that EF of v
function
is greater than
method.
0.
For a
To be
Preflow
the
f
sum
and
of
a
the
compatible
heights of all
labeling
nodes
h, we
with a
define
positive
a
axis.
phi of
V is often called a
h
potential,
is equals to the
since
summation
it
of
resembles
h of
the
v,
potential
summing for
energy
all
of all nodes with
v
a
such
positive
that
axis.
EF of v is greater than 0.
In the initial preflow and labeling, all nodes
To be
with
the
positive
sum,
axis are at height
that is a
0.
phi of
So phi
h
of
fh
is
to be the
equals
sum
to 0.
of the heights
Phi of
of the
fh
all
remains
nodes with
non-negative
positive axis.
throughout the
V
algorithm.
is often called a potential since it
non-saturating
resembles
push
the
of
potential energy of all
FHVW
nodes
operation
with positive
decreases the
axis.
phi of FH by
In the
at
initial
least 1,
preflow
since after the push
and
the
labeling,
node V
all
will
nodes
have no
with the
axis.
positive axis are at height
And
0.
W, the
So
only node that
phi
gets
of
new axis from the
FH
operation,
is equals to 0. Phi of
is at a height
FH
1 less
remains
than V.
non-negative
However,
throughout the
each
algorithm.
saturating push and each relabel operation
A
can
non-saturation
increase
proof
phi
of FHVW operation decreases
the
phi
relabel
of
operation
H
increases
by
phi of
at least 1,
fh by
since after the
exactly
push
1. They are
node
at most
V
two
will
n
have
squared
no
relabel
access.
operations. So the total
In
increase
W,
in
the
phi of
only node
fh
that gets new
due to
access
relabel
from the
operation is
at
2n
height
squared.
1 less than V.
A saturating push of
However, each
FHVW
slim and
operation
push
does not
and
change labels, but
each
it can
saturating
increase
push
phi of
and each
FH,
relabel operation
since
can
the node W
increase
may
phi
suddenly
of
acquire positive access
FH
after the
relabel
push.
operations, so the
This
total
would
increase
phi
of
of FH by
due to
the height
relabel
of W,
operations is
which
2 to
is
the
at
n
most
squared.
2m
The
minus
saturating
1.
push of
There are at most
FHVW
2nm
operation does not
saturating
change
push
labels,
operations,
but it
so the total
can
increase in phi of
increase phi
FH
of
due to
FH,
push operation
since
is
the
at
node
most
W may suddenly
2mn
acquire
times
positive
2m
access
minus
after
1.
the push.
So between
This
the
will
two
increase
clauses,
phi of FH by the
can
height of
increase
W,
by at most
which is at most 2n minus 1.
n squared
There
during
are
the
at most
algorithm.
2n times
But since
m
phi
saturating
remains
push
non-negative
operations,
throughout
so the
and
total
it
increase
decreases
is
by
phi of
at least 1
due to the push
on each
operations is
non-saturating
at
push
most
operation,
2n
it follows
times
that
m
there can
times
be
2n
at
minus
most
1.
4
So
n
between the
squared non-saturating push operations.
two causes, phi of
Extensions
can
and
increase by
improved
at
version
most
of the
4
algorithm.
times n
There
times
has
n
been a
squared
lot of work
during the
devoted
algorithm.
to
But since
choosing
the
node
V
selection
remains
rules for the
non-negative
preflow
throughout
push
and
algorithm
it
to
decreases
improve the
by
worst
at
case
least
running time.
one
Here we
on
consider
each
a
non-saturating
simple
path
rule
operation.
that leads to an improved
It follows
big O
that
of
there
n
can
cubed
be at
bound
most
on the
4
number of
n
non-saturating push
m times
operations.
n squared non-saturating
7.30
push
if
operations.
at each step we choose the node with access at maximum height, then the number of non-saturating push operations throughout the algorithm is at most 4n cubed. Proof. Consider the maximum height h equals to the maxima among h of v, where the maxima is chosen among all those index v such that ef of v is greater than 0. Now, once we choose the maximum height of any node with access as the algorithm proceeds, the analysis will use this maximum height h in place of the potential function phi in the previous big O of n squared times m bound. This maximum height can only increase due to relabeling, as flow is always pushed to nodes at lower height, and so the total increase in h throughout the algorithm is at most 2n squared. By 7.26, h starts out 0 and remains non-negative, so the number of times h changes is at most 4n squared. Now consider the behavior of the algorithm over a phase of time in which h remains constant. We claimed that each node can have at most one non-saturating push operation during this phase. Indeed, during this phase, flow is being pushed from nodes at height h to nodes at height h minus 1, and after a non-saturating push operation from v, it must receive flow from a node at height h plus 1 before we can push from it again. Since there are at most n non-saturating push operations between each change to h, and h changes at most 4n squared times, the total number of non-saturating push operations is at most 4n cubed. As a follow-up to 7.30, it is interesting to note that experimentally, the computational bottleneck of the method is the number of relabeling operations, and a better experimental running time is obtained by variants that work on increasing labels faster than one by one. This is a point that we pursue further in some of the exercises. Implementing the preflow push algorithm. Finally, we need to briefly discuss how to implement this algorithm efficiently. Maintaining a few simple data structures will allow us to effectively implement the operations of the algorithm in constant time each, and overall to implement the algorithm in time big O of mn plus the number of non-saturating push operations. Hence, the generic algorithm will run in big O of mn squared time, while the version that always selects the node at maximum height will run in big O of n cubed time. We can maintain all nodes with access on a simple list, and so we will be able to select a node with access in constant time. One has to be a bit more careful to be able to select a node with a maximum height h. in constant time. In order to do this, we will maintain a linked list of nodes with access at every possible height. Note that whenever a node V gets relabeled or continues to have a positive access after a push, it remains a node with a maximum height h. Thus, we only have to select a new node after a push when the current node V no longer has positive access. If node V was at height h, then the new node at maximum height will also be at height h, or if no node at height h has access, then the maximum height will be h minus 1, since the previous push operation out of V pushed the flow to a node at height h minus 1. Now assume we have selected a node V, and we need to select the edge VW on which to apply push of FHVW or a relabel of FHV if no such W exists. To be able to select an edge quickly, we will use the adjacency list representation of the graph. More precisely, we will maintain for each node V all possible edges leaving V in the residual graph, both forward and backward edges in a linked list, and with each edge we keep its capacity and flow value. Note that this way we have two copies of each edge in our data structure, a forward and a backward copy. These two copies will have pointers to each other, so that updates done at one copy can be carried over to the other one in big O of 1 time. We will select edges leaving a node V for push operations in the order they appear on nodes V's list. To facilitate this selection, we will maintain a pointer current of V for each node V to the last edge on the list that has been considered for a push operation. So if a node V no longer has access after a non-saturating push operation out of node V, the pointer current of V will stay at this edge, and we will use the same edge for the next push operation out of V. After a saturating push operation out of node V, we advance the current of V to the next edge on the list. The key observation is that after advancing the pointer current of V from an edge VW, we will not want to apply push to this edge again until we relabel V. 7.31. After the current of V pointer is advanced from an edge VW, we cannot apply push to this edge until V gets relabeled. Proof: at the moment the current of V is advanced from the edge VW, there is some reason push cannot be applied to this edge. Either h of W is greater than or equals to h of V, or the edge is not in the residual graph. In the first case, we clearly needed to relabel V before applying a push on this edge. In the later case, one needs to apply push to the reverse edge WV to make VW re-enter the residual graph. However, when we apply push to edge WV, then W is above V, and so V needs to be relabeled before one can push flow from V to W again. Since edges do not have to be considered again for push before relabeling, we get the following. 7.32. When the current of V pointer reaches the end of the edge list for V, the relabel operation can be applied to node V. After relabeling node V, we reset current of V to the first edge on the list and start considering edges again in the order they appear on this list. 7.33. The running time of the Preflow push algorithm implemented using the above data structures is a big O of mn plus big O of 1 for each non-saturating push operation. In particular, the generic Preflow push algorithm runs in big O of n squared m time, while the version where we always select the node at maximum height runs in big O of n cubed time. Proof: the initial flow and the relabeling is set up in big O of m time. Both push and relabel operations can be implemented in big O of 1 time once the operation has been selected. Consider a node V. We know that V can be relabeled at most 2n times throughout the algorithm. We will consider the total time the algorithm spends on finding the right edge on which to push flow out of node V. between 2 times that node V gets relabeled. If node V has a dV adjacent agencies, then by 7.32 we spend big O over dV time on advancing the current of V pointer between consecutive relabelings of V, thus the total time spent on advancing the current pointers throughout the algorithm is big O of the summations of n times dV summing for all little v in capital V, which is equals to big O of m times n as claimed. So that's why we always select the node at maximum height runs in big O of n cube time.